pleasure to have Professor Snoek for today's as a speaker today. So Professor Snoek is a full professor in the computer science department at the University of Amsterdam, and he is where he is the video and image society. He's also the director of many research AI labs in cross industry and research institutions. Without further ado, please join me welcome Professor Snoek.
Thanks so much for having me. When I was younger, I was talking about what my new models could do at these type of events. And nowadays, I can only talk about what other people's models can no longer do. So that is the topic of today's talk. Let's have a brief look at history. About 500 million years ago, our planet was occupied by life forms like worms, sponges, and jellyfish. And this was about the diversity of intelligence on our planet. Then at some moment in time, the so-called Cambrian explosion happened. And it caused a huge diversity in all kinds of life forms on our planet. This was sort of like the biological big bang. All of a sudden, life forms at our planet got armors, they developed tentacles, and so on. And it is still sort of a mystery of what caused this. But likely it became very light on our planet, and light receptors started to develop. So life forms got eyes, developed intelligence, and all of a sudden life was about eating or being eaten. So it was also important to protect yourself, to develop all kinds of skills and to be able to move around. So that's how life forms developed. We make a small jump. If we look at human intelligence, about 50% of our brain capacity is spent on seeing. So I would argue, and I think I'm at the right venue today, that computer vision, that vision is crucial for human intelligence. The human invention of written language is of a much more recent time, so most likely developed in the Middle East, in Babylon, nowadays Mesopotamia, the area known as Iraq nowadays. And writing language develops over multiple cultures, over multiple years to what we have today. Since the human invention of ChatGPT, we all believe that human intelligence is all based on language. Of course, it is very important, and its results have been amazing. Can't make it less. But OpenAI actually has made more interesting models. So you're probably all familiar with the CLIP model that takes multimodal perception into account. So combining language with vision is even more powerful than language alone. Now let's have a look at what people have been doing. This is the Flamingo model, and it really works well in vision and language. It has a few amazing abilities. So based on a few in context presented examples, it can essentially solve any vision task. So each of these rows used to be a PhD student for 4 years. So a PhD student could work on object recognition, like, so you give it a few examples. This is a chinchilla together with a photo. This is a Shiba, they are very popular in Japan. Then you would give it a photo, this is, and a flamingo. And the Flamingo model can do this out of the box. But by simply changing the examples, right? So now we go to the third row and we say we give this an example, and the output is underground, and the second example is street sign. You say the output is Congress, and all of a sudden this foundation model can do OCR, right? So this used to be a PhD project for 4 years. You could work on OCR recognition. Now all of a sudden one model can all do all these tasks out of the blue. So this is amazing. Look at the last row, where it can do arithmetic based on pixels and text. It's really very impressive. Here's another model called Blip2. It's from June last year. This also has some very nice capabilities. For example, you presented the photo on the left, and then you ask, is this photo unusual? And then it says, yes, it's a house that looks like it's upside down. And then, okay, I see that too. But then when I saw the next answer, I really had to look at the picture again to indeed verify that there is a slide on the side of the house. I didn't actually see that myself when I first looked at the house that is upside down. And this model figured it out, so pretty impressive. The photo on the right is also interesting because you ask what is shown in the photo, a man and a chicken. Now it is not really a chicken, it's more like a rooster. So okay, that is not so correct. But then the second interaction asks for what does the man feel and why? And then Blip2 says, well, he's scared of the chicken because it's flying at him. So that is some quite interesting ability that we have over here. I'm going to talk what these models cannot do yet, and I've structured the talk into 4 parts. If we get to all of them, I want to talk about scarcity, a problem that these models cannot handle well, space, time, and also human values. Now, the first topic I want to discuss is scarcity, and this is based on a joint work that is presented at this conference together with Yunhua Zhang and Hazel Doughty, and it considers low resource computer vision. Many developments nowadays happen first in NLP because they were doing large models first. So it's a very good source of inspiration. And we have noticed that low resource language processing is very popular in NLP because many of these large language models are great for Mandarin, for English, for Spanish. But when you get to more smaller languages like Dutch, all of a sudden their capabilities become less impressive. So we were wondering, is there also a low resource equivalent in computer vision, and what would it be? So in computer vision, we have been very good in collecting big data, and it has certain properties. So it is typically rather coarse-grained. So let's think ImageNet, right? It's a huge collection of data, but the categories are rather coarse-grained. It is big data, and the domain is very general. Typically, what you can find on the internet, on photo sharing websites, what have we. Now, on the other side of the spectrum, on each of these dimensions, we have for low resource, there are a few properties. The first one, it is typically very limited data. So we have small amounts of images. And then typically the content of these images is very fine grained, so very specialized. So the domain is very specialized, requiring lots of knowledge to be able to interpret these images. Now, all of these aspects have been studied in isolation in our community. We have looked at limited data, we have looked at fine grained recognition, we have looked at specialized domain, but not in combination. And that is what makes low resource computer vision interesting. To give you some examples. Here are some typical scenarios that we consider low resource. So if you had electrical engineering in your education, you might be familiar with these diagrams. These are circuit diagrams. The one on the left presents a pictorial representation of a circuit, and the right interpretation of this circuit is that it functions as an audio amplifier. Now, you won't find a huge amounts of these type of images on the internet. Here's another scenario and an appropriate task, historic map retrieval. So here we look at the problem of, given a historic map of an old city, let's say somewhere in Europe, can you find the modern day equivalent of this map using Google Maps, for example? And the third example that we have is mechanical drawing retrieval. So given a 3D rendered image, can you find a three-dimensional view drawing? Now, we built a benchmark for those 3 data sets and those 3 tasks. And what you will notice is that for each of these tasks, the number of train, validation, and test images is really rather small. right? So much smaller than we are used to working with. And although we did our best to collect as many images as possible online, it's still rather small for modern standards. Now, the first thing that we wanted to do is establish that indeed this is a problem that large-scale foundation models cannot solve out of the box, right? So we took a few models off the shelf and applied them on our models or on our data sets and benchmarks. So here you see for the three different tasks, so circuit diagram classification, historic map retrieval, and mechanical drawing retrieval, you see the performance of four present-day foundation models. So we tested CLIP, SAM, ImageBind, and BLIP. So ImageBind is from CVPR last year. And as you can see, all these bar graphs indicate that the performance of these models is rather poor. So it is in the order of, recall at one of at max 20%. So really poor performance. And several of these models actually perform close to zero. So this means that they are not really suitable for these low resource problems. Now, what are now exactly the challenges that we are interested in low resource computer vision is that, well, there are basically three. So there is data scarcity. So you cannot train from scratch and make your system capable of low resource. The content of these images is rather fine-grained. So you need a very nuanced representation. And also the domain is very, very specialized. Now, what we're trying to do in this work is to given an existing foundation model, come up with simple adapters that can sort of like make these models more suitable for the low resource computer vision scenario. So what we propose then is three simple baselines that provide a first indication that this is indeed feasible as an encouragement for the community to pick up this problem and improve upon it further. So I will briefly go over these simple baselines, though the first one is that we generate data to account for the data scarcity of these low resource domains. So of course we rely on generative AI, in this case stable diffusion, and we use the stable diffusion in two ways. So the first one is the obvious. We generate more of the same data, so data that looks similar to the data that we already have. But if you only rely on this type of data, your fine-tuning operation will start to overfit. So it will not generalize well. So just generating more like this data won't bring you very far. So what we also did is what we call, we augment the data by breaking the labels. So we generate data in a similar style as the images we already have, but with no means to preserve the categorical information in these images. Now, if you do this multiple times, you get sets of images that no longer look like the ones you had in your training set, but the ones that are generated start to become very similar. And these are useful examples for fine-tuning. Although they have no label, you can still use them as examples. So here are this is what I mean. So on the left, you see what you would get with like off-the-shelf stable diffusion of generating more of the same. This is what we call label preserving examples. And then on the right, you see what we call label breaking generated examples. So by doing so, we get more examples and get a richer diversity that helps for fine-tuning. The second simple baseline that we added is that we look into tokenization for fine-grained recognition to be able to capture more fine-grained details. We have limited data, so we cannot pre-train from cannot train a tokenization layer from scratch. So instead, what we do, we divide the linear projection kernel into multiple subkernels, and then for each of these subkernels, we introduce a weight, and that weight we can optimize with the limited examples that we have. And by doing so, we create patch-level features with a learned weighting that allows to incorporate these fine-grained details. And then the third one is that we look into the attention mechanism of the transformer architecture, and we look for particular patterns in the image that we want to incorporate also in the attention mechanism. How do we do so? We introduce, for each token, we crop its region from the global attention map, and we combine this with the multi-head self-attention. Now, in the paper, we show that each of these simple baselines that we added indeed makes foundation models better equipped for low resource scenarios. Details are in the paper. I want to highlight one result. So when we combine those three baselines together, so we have the subkernels, the attention mechanism, and the data generation combined. That is what you see displayed over here for the task of historical map retrieval. You see that the zero-shot transfer from CLIP is rather poor, but when you add our baseline, there is a large jump. The line in blue is an off-the-shelf adaptation method, but that is not optimized for low resource, right? So low resource is really a different type of problem and requires a different type of solution. Here are some qualitative results of our approach, especially where it fails. So what we notice is that our predictions are, because they have limited examples, they tend to be overconfident. So there is still some amount of overfitting happening. And very often these predictions are based on a key region in the image, such as the presence of the battery in a LED circuit, which triggers strong confidence. We also noticed that if these low resource settings are not only do they have few examples, they are also long-tailed. So some styles, for example, in the historical maps are so rare that we meet them at test time, but we never saw them at training time, and then the methods also fail. So that's really challenging still. So what can multimodal foundation models not perceive? Well, they cannot perceive under scarcity constraints. Then they start to sort of like become brittle. Next, we're going to look into spatial aspects of multimodal foundation models. And this is a work that will also be presented at this conference on Thursday, joint work together with Michael Dorkenwald, Nimrod Badarzani, and Yuki Asano, where we look into the localization ability of caption-based vision language models. Of course, this community has developed wonderful specialized object localization and detection methods. They are super effective in identifying objects, segmenting them on a pixel precise level, but they require huge amounts of annotations, and they can only do this specialized thing. We looked instead in vision language models like Flamingo and Blip, and we probed how well they are able to localize objects of interest out of the box, right? So here we have a typical query with an image. So the prompt here is provide a bounding box around the person in the image. Here is the results of some off-the-shelf vision language models. So as you can tell, so OpenFlamingo, Fromage, and Blip2 all have no clue what to make out of this. So they cannot add localization ability out of the box. We also tried GPT for vision, and that one is able to generate a bounding box. We don't know what was the training data of GPT for vision. Likely, it has also used bounding box annotations. But notice it is still not very precise. Here are some more examples. So arguably, the image with the dog is easy because there's only a single object and it's in the center of the image. The third image is more challenging because there are multiple objects, so you need to be able to figure out which one is the one that is really prompted here. And again, these existing foundation models don't do a really good job. We also tried slightly different prompts, for example, providing a grid structure over the image so that the language model can prompt the grid cells that encapsulate the object, but it also didn't work at all. We also tried chessboard-like patterns because maybe it has seen lots of chess games being played in its training data, so that we can use sort of like the chess coordinates to identify the object, but that also failed miserably. We did one more test for spatial reasoning. So given the location of the pizza, can the language model identify what is above, left, right, or below? We see some mixed results. So sometimes the objects are well identified, but cannot choose between this is the dog and the shark or one of them, but still not very convincing, I would say. Now, of course, you can retrain from scratch with huge amounts of box annotations, but instead we follow a different route, and we thought, well, assuming that there is a huge amount of knowledge encapsulated in these vision language models as captured in their huge parameters, what can we do to sort of like leverage this knowledge without retraining it from scratch? So we are looking for a small intervention in the model so as to equip the model with this localization ability. And that is what we call a PIN. So given a vision language model, let's say Flamingo, we add our PIN module together with a self-generated supervision signal to enable localization in these models. That is the basic idea. So this is Flamingo, high level. So how does Flamingo work? You have an image, it's passed through a vision encoder, is combined with the embedding of a large language model in this fusion network, which is a perceiver model. And then this is optimized as a next token prediction challenge. So in the image is the prompt, and then the system needs to predict that there is a monkey. Now, our PIN module is inserted after the vision encoder, and basically it contains two things. The first one is a constant sinusoidal embedding. So this is 64 dimensions, and then a very simple two-layer MLP is being added. This MLP contains about 1 million parameters in total, and you have to take into account that the overall number of parameters in Flamingo is in size of 3 billion. So that is less than, that's about 0.3% of parameters that is being added. This is the architecture. Then we still need to have a mechanism to fine-tune to get localization abilities without providing human annotated data, right? And that is where our self-generated supervision signal comes in. So we again rely on stable diffusion to generate objects, and we paste these objects into images that are obtained from a scenery data set, so with background scenes. So how does that work? You have a generated object of a monkey together with the background scene image, and you simply paste the object image somewhere in the scene. And because you have full control on where you paste, you also have full control on the box locations. So this provides you with box location annotations. You can do that for multiple objects, also multiple at the same time, etc. So during training, we have our self-generated supervision signal together with the vision language model and our PIN module. And then we formulate localization, so outputting the box coordinations also as a next token prediction task. So we are now in the language space, and we ask the VLM to output box coordination word, so to say. And only the MLP parameters here are being optimized. Then at inference, you feed the VLM with an image together with a prompt that has to indicate what is the object you are interested in. We cannot do categorization, we can only do localization. So here you ask, in the image is the banana located at? And then if all works out as planned, it will give you the coordination of the box encapsulating the bananas. This works well. So we can localize any object in images. So here is some manifestation of this ability. Of course, not as good as specialized object localization methods, but the point of this paper was to demonstrate that we can sort of like enable this new ability by small intervention. We did compare with other parameter efficient fine-tuning methods that are known, like LoRa and visual prompt tuning. But in all cases, our pin module performed better, and we tried this for both OpenFlamingo and Blip2. That was space. Then next, I want to talk about time. So temporal awareness of foundation models. This is a work from CVPR last year, together with Piyush Bhatt and Makaran Tapasvi. So this is a typical vision language model. What does this picture show? And then the vision language model can tell you, well, a dog running. And this is particularly attractive for video models because of the huge amount of data, cumbersome to annotate. So it is a great resource to label video frames. It can do things like, what does this video show? And it will tell you a kid eating ice cream. Now, we ask ourselves the question, do these video foundation models really understand time, or are they just image language models on steroids, right? So they just identify a single frame in the video and predict what is the video about based on the interpretation of this single frame. So if we only show this image, the model will also say a kid eating ice cream. We don't know whether there's actually any temporal understanding or reasoning abilities. So Piyush had a very nice idea. So rather than asking what is in the video, he asked what he called test of time questions. And these are questions that have temporal relationships. And we focused on very simple questions. So we only considered before and after questions. So now the question becomes, the baby eats ice cream before walking downhill, true or false? And then all the video language model has to do is say it's true or it's false. Now, we created a benchmark with artificial synthetic data, where we created several shapes with several colors. And we defined sentences like a red circle appears before a yellow circle, which is the correct sentence. And we also did the opposite. A yellow circle appears before a red circle, which is the wrong one. And we simply asked several video language model, is this sentence given this video, is it correct? Right? So is this before or after relationship correct? Since this data is rather artificial, and we wanted to make sure that this was not causing the disturbance in the models, we also had a control test, same type of data, but without any before and after relationships. So here we just, the model has to say, a red circle appears, and it has to say true or false in this case. Now, much to our surprise, at that moment in time, many of the existing video language models had no clue what to do with these before or after relationships. So they perform as good as chance. So implying that they have no temporal understanding whatsoever, which is quite surprising for a video language model. And the control task they could do very well. So it was not related to the data. So again, we questioned, can we then instill this notion of time awareness in existing video language model without doing without retraining it from scratch, right? Because video amounts are humongous. We are a small university. We don't have a lot of compute to redo all this. We have to be clever. So we defined this notion of post pre-training, essentially another round of pre-training on top of a pre-trained video language model. And we made smart use of existing data by simply using the fact that we have these dense video captioning data sets that have segments and sentences associated with them. And by, again, using before and after relationships, you can connect two segments, two sentences with a before or after connector, create positive example, and you can turn this around to create negative examples. So by doing so, we could quickly generate temporal aware training data from existing sources. So no manual labeling whatsoever needed. We took a video clip model that is based on a S3D feature. So this is the architecture of this model. So pretty standard. And then our post-pre-training procedure is contrastive learning. So fairly simple. You have videos and sentences, and the goal is to optimize the right sentence with the right video. This is the traditional contrastive learning. Because we have these sentences with before and after relationship, we have extra options, right? We can create hard negative examples by switching the before and after statement. And at the same way, we can also flip the videos to create more positives. So we have more data. We run this post-pre-training procedure on top of video clip, and we perform a set of experiments on several well-known data sets. So tempo, Create, Ego, and ActivityNet, selected based on their presumed way of modeling temporal information. Here you see some of the results. On the y-axis, the ability to do temporal ordering, so in our test of time setting, and on the x-axis, the retrieval performance that was used in these Q&A data sets. So the sweet spot is in the top right corner. Now here you see what happens. So in red, the baseline video clip performance, and after our post pre-training procedure, the results indeed move closer to the sweet spot where we want to be. Depending on the data sets, the impact of the result varies. So on some data sets, we get a bigger boost than on others, but on all 4 data sets, the trend is the same. So after our post-pre-training adaptation, the video clip model becomes more time aware. So we have injected this ability, so to say. So I discussed scarcity, space, and time to inject in multimodal foundation models. The last one I want to talk about is human values. So can we, in the same way as we can inject spatial properties, scarcity properties, and temporal properties, can we also inject human values in these models, and how to do that? I don't have the solution to that one yet. This is more like a work in progress, but I want to present it anyway for discussion. So multimodal foundation models are great, but they have a few negative effects that are becoming more and more clear. This is a devastating picture from a car crash with a self-driving car that crashed upon a pedestrian that was crossing the road and was not recognized by the perception software of the car. So this is a huge problem. How can we bring these models in society when they create these kind of devastating effects, and how to circumvent, how to handle, how to build a society on top of this, right? Given these developments. Unknown. This is a photo of a explosion near the Pentagon that appeared on X, and it created the New York Stock Exchange to go down. And the American authorities felt obliged to make a statement to say that this is a deep fake. It's fake news, right? So it looked so realistic that people started to act, think, oh my God, I have to sell my stock because now World War III is going to start. So it was fake news. So how to handle these realistic abilities of foundation models, unknown. These are results that were generated by Gemini. So I think the Gemini team needs to be applauded for taking diversity into account and making sure that outputs are really representative for all cultures and all over the world. But here it is being abused in sort of like changing history, the course of history, which is a little bit weird. So this had to be taken offline because it was hallucinating results that were not acceptable for such a platform. I don't envy them. How to do this well is super complicated. Big challenge, I think. Last but not least, at the end of the day, our computer vision software ends up in a camera. They are being installed in public spaces. You see two typical examples, one from my hometown, maybe one from your hometown. And this also has very interesting questions that comes about, like who owns the data, who is responsible for the software, what is being done with this data, who handles my privacy, what about, right? We need to think about this. So we started Hava Lab to think about what defines these human-aligned foundation models. How can they make computer and what determines especially societal acceptance, right? Because what we are creating is starting to work and is being deployed in society. So we have a responsibility to also think about this deployment. And I found a really nice set of collaborators at the University of Amsterdam, and almost nobody is a computer scientist. But they also have opinions about vision and deployment in society, the ethical values, the legal frameworks, use cases like in surgery and in public safety. So we're going to look at this the coming years. So I hope to present that in a future talk. But I think it's a very important topic that our community should embrace. With that encouragement, I would like to conclude is that, first of all, multimodal foundation models, I think, are really amazing. So don't get me wrong, I'm not a criticaster of foundation models. I'm a big fan, but they have several perceptual difficulties, most notably the ones related to scarcity, space, time, and the lack of alignment with human values. We demonstrated that small capacity adapters, so with a relatively small number of parameters and clever use of synthetic data, you can sort of like instill these properties into these models with a relatively small computational footprint. So this brings a nice bonus of being both sustainable and also responsible. So there is still a lot of hope to do it right, so to say. And with those words, I would like to thank you for your attention.